All right, so remember that in section 311 we're talking about the hyperbolic functions. The hyperbolic functions were defined in terms of the exponentials, e to the x and e to the negative x, and we call it the graphs of at least the hyperbolic cosine, hyperbolic sine, and hyperbolic tangent looked as follows. So today we want to look at the inverse hyperbolic functions. Okay, and so notice that the sine, the hyperbolic sine and the hyperbolic tangent are both pass the horizontal line test, right? They both pass the horizontal line test. So those are both one-to-one functions and pretty clearly have inverses because they're one-to-one. However, the hyperbolic cosine, okay, fails the vertical line test. So we are going to have to restrict the domain of the hyperbolic cosine and be able to get an inverse. Okay, and we'll go ahead and restrict it to this right half. Okay, if we cut off the left half and just have the right half, that side of it would pass the horizontal line test, and then we would be able to invert it. Okay, so the hyperbolic sine and the hyperbolic tangent are both one-to-one, so they clearly have inverses. But we have to do a little work to get the inverse of a hyperbolic sine. We have to restrict the domain to the right side of that graph. Okay, so the inverse hyperbolic sine, cosine, and tangent have very similar notation, so it shouldn't throw you off at all. We just have the little superscript of the -1 to show the inverse functions there. And so the inverse hyperbolic sine just means that, okay, if I were to take and ask what is the angle that would give me a hyperbolic, or the value that would give me a hyperbolic sine value of x, right? All right, so notice the only tricky part is that we have to make sure that we put that y is greater than or equal to 0 in the hyperbolic, the inverse hyperbolic cosine. Okay, and then again, as you would expect, if you think about, okay, let's say I had, you know, the line y equals x, the 45-degree line there, we know that to find an inverse, the graph of it would just be the reflection over that. So if I were to reflect, okay, this over the 45-degree line, this would come down and follow me x-axis, and it would go like this, right? So it's not surprising that we get this as our graph of the inverse hyperbolic cosine. Okay, if I were to put a 45-degree line in here, okay, this one reflected over that would just kind of look like that, and this one reflected over the 45-degree line would look kind of like this. Okay, and so our that's kind of what we expected, this kind of shape in the first quadrant and this kind of shape in the third quadrant. So that's going to be the graph of the inverse hyperbolic sine. And then for the tangent, again, if I put a 45-degree line in there, this one's going to kind of come up like this, and then in the third quadrant, okay, it's going to kind of come down like this. And so that inverse hyperbolic tangent has a graph that looks like we would expect. Okay, so those are the definitions of the inverse hyperbolic functions. Okay, and since the hyperbolic functions are defined in terms of exponentials, it shouldn't be too surprising that the inverse hyperbolic functions can be defined in terms of logarithms, because logarithms are the inverses of exponentials, right? So let's say that we want to find an expression for the inverse sine, hyperbolic sine. Okay, so let's say that we have y equals the inverse hyperbolic sine of x. Okay, well, by definition, okay, that means that the hyperbolic sine of y is equal to x, right? That's what that inverse hyperbolic sine means. Okay, so let's say we had to find the derivative of this. So we can replace inverse hyperbolic sine of y with its definition of, well, that's e to the y minus e to the negative y over 2. Okay, and so now we just need to come up with an expression for it, basically to solve for whatever y is. So to solve for y, we'll multiply both sides by 2. We get e to the y minus e to the negative y equals 2x. Okay, just in the interest of making things easier, let's go ahead and multiply everything by e to the y to get rid of any negative exponents, because negative exponents means we have to deal with fractions, and we don't really want to deal with fractions. So let's multiply everything by e to the y. So we'll get e to the 2y minus 1 equals 2x e to the y. And let's go ahead and pull everything to one side of the equation and set this equal to 0. So this is going to be, well, let me pull this one over. No, I want to do e to the 2y minus 2x e to the y minus 1 equals 0. Okay. And now I'm just going to rewrite this a little so that you can see how we might go about solving this. So I'm going to write this as e to the y squared minus 2x times e to the y. I'm just adding parentheses, nothing special there, minus 1 equals 0. So if you think about it, this is written in the form of a quadratic. You know, we've got something squared minus a coefficient times that something, right? This is, you know, let's say if k was e to the y, I could rewrite this as k squared minus 2xk minus 1 equals 0. So I can use the quadratic formula to solve for k. So k is going to be negative b, so that's the coefficient here, so that would be 2x plus or minus the square root of b squared, so that's going to be 4x squared minus 4 times a, which is 1, times c, which is negative 1, all over 2a, over 2 times 1. Okay, so our k, which is really e to the y, is equal to 2x plus or minus the square root of, and this will be 4x squared plus 4, all of this over 2. I'm going to have to go up here. So I've got 2x plus or minus, okay, I can factor out a 4, and I know the square root of 4 is 2, so I can bring a 2 out of that square root, and I'll be left with x squared plus 1 under the radical, 2 in a denominator, and all those 2's can cancel, so I'll have e to the y is x plus or minus the square root of x squared plus 1. Okay, now one thing to note is that e to the y is always a number that's greater than 0. Okay, if you think about the graph of e to the y, no matter, you know, it looks like that, right? And it has to be greater than 0. Okay, so I have to ensure that whatever expression over here is also greater than 0, or they can't be equal. So if I think about this, x minus the square root of x squared plus 1, well, since x squared plus 1 is bigger than x squared, the square root is going to be just slightly bigger than x. And so I'm going to have a number x minus something just slightly bigger than x. So I know I'm going to have to get a negative value. This is going to be less than 0. So that means that e to the y can't be equal to x minus the square root of x squared plus 1, because we know this one has to be positive and this other one has to be negative. So the only way that the only solution to this equation that is valid, that's not extraneous, is the e to the y equals x plus the square root of x squared plus 1. Okay, and so then to solve for y, we just take the natural log of both sides, and we'll get y equals the natural log of x plus the square root of x squared plus 1. Okay, so y was also equal to the inverse hyperbolic sine, right? So this is the inverse hyperbolic sine of x. So that's how you would write it in terms of logarithms. And again, that shouldn't surprise us that we can write it in terms of a logs of x, because logs are inverses of exponentials. Okay, we could go through this process for all of the other inverse functions, but rather than that, you'll probably get to just do those as homework. So this expression that we derived is the expression for the inverse hyperbolic sine, and we have fairly similar one for the hyperbolic cosine. Notice the only difference that we have in here is the -1 instead of +1. Okay, which shouldn't surprise us too much because of the difference between the minus and the plus in the hyperbolic sine and hyperbolic cosine definitions. Okay, so that's why that one's different. And then, of course, for the hyperbolic tangent, we're just going to have to divide the function, so that those are going to be a little bit different. And so the square roots go away. All right, so we should, now that we know expressions for the derivatives of the inverse, or for the inverse hyperbolic functions, we, of course, are going to want to differentiate them. Okay, so we need to find the derivative of the inverse hyperbolic sine. Okay, so the derivative of the inverse hyperbolic sine. Okay, well, from the previous page, we know that the inverse hyperbolic sine is the same thing as the natural log of x plus the square root of x squared plus 1. So it's the same thing as taking the derivative of that expression. All right, so maybe not the prettiest, but we know how to do it. Okay, we've got a composition of functions, so we just need to use the chain rule. Okay, so what is the derivative of the natural log? Okay, well, the derivative of natural log is 1 over whatever we're taking the natural log of, which happens to be x plus the square root of x squared plus 1. Okay. Okay, so that would be the derivative, and then we got to do times the derivative of this function. So times the derivative of x plus the square root of x squared plus 1. All right, so the derivative of that sum will be the sum of the derivatives. So we'll get the derivative of x is just 1, and the derivative of the square root of x squared plus 1 will be 1/2. Okay, and then x squared plus 1 to the negative 1/2, so that'll put that square root in the denominator, times the derivative of the inside function. Okay, so times 2x. Those 2's cancel out. Okay, let's rewrite this sum as a single fraction. So think of this as being the square root of x squared plus 1 over the square root of x squared plus 1. So we're going to have 1 over x plus the square root of x squared plus 1 times, okay, so if we add these two things that now have a common denominator, I'm going to get x squared, the square root of x squared plus 1 plus this numerator over here, which is x, all over the common denominator of square root of x squared plus 1. Okay. And now we see that this numerator here is exactly the same as this denominator here. So those can cancel, and we just get 1 over the square root of x squared plus 1. Okay, so that means that the derivative of the inverse sine of x is equal to 1 over the square root of x squared plus 1. Okay. Now there's actually another way to solve this. Okay, and you may think that this one is easier, we'll have to see, but that's using implicit differentiation, so this is a good way for us to practice using our implicit differentiation anyways. Okay, so we can start with y equals the inverse hyperbolic sine of x, and we know that that's the same thing as x equals the hyperbolic sine of y. And now, instead of substituting in an expression, okay, we're going to go ahead and do implicit differentiation. So we're going to take the derivative with respect to x. So here we'll get 1. Okay, the derivative of the hyperbolic sine is hyperbolic cosine, okay, of y, and then times the derivative of the inside function, and that will just be dy dx. And so this is 1 over the hyperbolic cosine is the derivative. Okay. Now we want to put it in terms of x, so we need to do a little bit of work on this side to rewrite this. Okay, so if we think about the hyperbolic identity, we know that the hyperbolic cosine squared of y minus the hyperbolic sine squared of y equals 1. And so the hyperbolic cosine of y equals 1 plus the hyperbolic sine squared of y. And then if I take the square root of both sides, I'll get that the hyperbolic cosine of y equals, now you might think we should put plus or minus, okay, but we need to recognize that this, the hyperbolic cosine of y, if we go back to our graph of hyperbolic cosine of y, let me see if I can find it. Here it is. Okay, it's always a positive number. It's never negative. Okay, so we don't have to worry about a negative version. Okay, so this can only be a positive number, so we only have to consider the principal square root 1 plus hyperbolic sine squared of x. Okay, so we can make that substitution for the hyperbolic sine of y, or cosine. So this will be 1 plus hyperbolic sine squared of y. Okay, and notice that the hyperbolic sine of y is just x. So we can substitute x in for hyperbolic sine, and this will be 1 over 1 plus x squared is the derivative. Okay, which gives us exactly the same thing that we got before. So either way, we can use implicit differentiation or the differentiation straight from the logarithmic definition. This one definitely has a lot of room for error because you have to remember to use the chain rule multiple times and such. This one just has the trick of having to come up with a nice expression for hyperbolic cosine to make this a substitution. So either way, you look at it, you get the same thing. The derivative of the inverse hyperbolic sine is always going to be 1 over the square root of x squared plus 1. Okay, now of course we could go through the process for all of the inverse hyperbolic functions, but again, we'll leave that as an exercise for homework. You'll get a chance to do some of those. So we did this one. Not too surprisingly, the hyperbolic cosine derivative isn't very much different, just a little bit of a sign change there. And again, you'll just have to go through the process to verify the rest of them. Okay, so the last problem we want to do is look at, let's say that we actually know what all of the derivatives are, and we want to find the derivative of the inverse hyperbolic tangent of the sine of x. Okay, so this is a composition of functions. This one is on the inside. sine is, and the inverse hyperbolic tangent is on the outside. Okay, and so when I do this, I have to start with the outside. So the derivative of inverse hyperbolic tangent is 1 over 1 minus whatever the argument to the inverse hyperbolic tangent is. So I'm going to do 1 over 1 minus, and then the argument, sine of x squared. Okay, so I'm just taking that sine of x that was the argument to my inverse hyperbolic tangent and putting that in. Okay, and now chain rule says I have to do times the derivative of that inside function. So I need to do times the derivative of sine. The derivative of sine is cosine. Okay, so I have 1 over 1 minus sine squared. Well, we know that 1 minus sine squared is the same thing as cosine squared. So I have cosine squared times cosine. So one of those is going to cancel out. I'll have 1 over cosine, which is the same thing as secant x. Okay. All right. So that wraps up chapter 3. All sorts of different derivatives. So now you just need to practice lots and lots of derivatives.